Hey guys, welcome back to Speedrunning Math Season 2 Statistics Episode 5. My name is Ariston, and in this series, we do math together. At the moment, we are currently doing statistics, and we're doing pretty introductory level statistics just so that you, the viewer, can learn alongside me, and so that I get a refresher as well, because the foundations to anything are always very fundamental, hence the name Foundations. Um, I just wanted to give a quick update for regular viewers of the channel. We're at 86 subscribers now. It's pretty crazy because I started this channel 3 months ago, and in the first, I'm gonna say, month and a half, we had like 4 subscribers, dude. I got a couple of comments here and there, which are really nice, but I never started this channel thinking about the viewers. I never did this for anyone, and as of late, I feel that that's changed, and I've kind of forgotten why I've started the channel. And that's not to say, oh, boo-hoo, what's so bad about that? I just want to talk about how sometimes we go through life, we stray away from the path, and quote unquote, the path might be different for you. But for me in this case, I thought I was locked in. I felt locked in, and then I broke my Khan Academy streak. I was trying to shoot this episode yesterday, but I just got so heartbroken by the fact that it escaped my awareness, it escaped my knowledge, that I hadn't done a single math problem in 8 days, which is a big no-no because this year I wanted to, and I have been, just not for the past 8 days, which is pretty bad in my opinion. You might not think it's a big deal to not do math for 8 days, but it's the same sentiment as skipping the gym. You skip the gym for a day, 2 days, 3 days, then a week, and then 2 weeks, and then where do you draw the line of I've fallen off, you know? So for me, it's a good thing that that happened, that my streak broke, and that I took pride in the streak because it's a reminder that, oh dude, you're falling off. It's been more than a week since you last done math, and you really like math. Like, why aren't you doing more math? As of late, there have been so many unimportant, less important things, distractions that have been distracting me from the things that actually matter. Mather. So, yeah, this year and starting today, I want to lock in, as people usually say nowadays, and always remind myself, always keep it at the forefront of my mind. What is important? Is this important? Is how I'm spending my time wise? Am I spending it on the things that actually do matter to me? Because in this life, guys, there are so many distractions and unimportant things that we either lie to ourselves are important or we just don't think hard enough to see that they're not. Anyways, this is probably one of my most serious, longest intros. This isn't even the message of the day yet, but we're gonna get right into that now. Whoops, forgot the new trick. The message I want to share with you today is that people are often unaware of their own unawareness. Sounds like a mind bleep. Can't swear on this channel anymore. Just something I'm working on. And people that go to the gym and they skip a day and then a week and then 2 weeks and then it's been a month and they're out of shape. They aren't aware that it's happening in real time. If they were, if they saw the gravity, the magnitude of their actions, they wouldn't. If they saw where they'd be 2 months from then, if they could travel in time and see them being 10 kgs heavier, they would be like, "Oh God, I gotta change." But people often don't. People might just not think about it. Life might happen. For me, it was math. I thought I was locked in, doing the data science, doing the programming, but in all honesty, I haven't been. My upload frequency has more than halved, halved, yeah, halved, and it's only up to myself to determine where I draw the line of I'm falling off. If I talk to my parents about it, if I talk to my friends about it, they might be, "Oh, no, you're being too hard on yourself, bro." That's cope. That's not what I set out to do. I set out to do math every day, data science every day, and if not every day, every other day. But it's been 8 days. So we have to keep ourselves accountable. We have to keep track because what we do not track, we cannot manage. So always keep in mind, you might be unaware of something you're unaware about. Let's get right into the math. 631. That was super long. That doesn't matter. Another thing that I need to change is that my I haven't been one-shotting the videos. I think that's quite bad. That's quite bad because the whole purpose of this channel is for me. Me improving my delivery, me improving my... Have we done this? We have. Okay. Hmm. 5 questions. Have we done this? Yeah, we have. Again, going back to what I was saying, it's not nearly as important as just me doing the
An
math,
ecologist surveys the age of about 100
me
trees in a
explaining
local forest.
stuff,
He uses a box and whisker plot to map his data, shown below. What is the
me
range of
talking
tree ages that
like
he surveyed? What is the median age of a tree in the forest? So first
a
of all, let's make sure we
narrator,
understand what this box and whiskers plot is
learning
going
how
to do.
to
This
at
is really a way of
least,
seeing the
or
spread of all of
trying.
the different data
That's
points
just
in the distribution tree.
secondary.
This is the box, and then this is another whisker right.
Okay, this is a box plot. What is a box plot? It is a... What kind of distributions do we have? We have frequency. We have... Oh, let's timestamp this as well. I feel that we've done box plots before. Okay, so this little segment is on box plots and how to interpret them. So the full name of a box plot is a box and whisker plot. We have these whiskers on the end, as seen by these little lines, and the horizontal lines that stick out. And so let's dissect a box plot, a box and whiskers plot from outside to inside. These two horizontal lines at the very far ends, on the left and right. And box plots could also be vertical, so same would apply, just do it vertically. But these lines at the end indicate the minimum and maximum values within a data set. So here it would be 50, and
over here.
I can't see this because of that, and 8. And then these three bigger lines would be what we call the quartiles. There are 3 quartiles, the 25th, the 50th, and the 75th. The 50th quartile, 50% quartile, is also known as the median, and you might know that as just the middle value of the dataset. And if there are two middle values, because it's an even number of data points, you get the value in between those two middle values, so you get the mean. And for the 25th and this, I guess we could just call them the first, second, and third quartiles, because that's what a quartile means, right? Quarter, 25%. The first and third quartiles are just the medians off the left hand and the right hand side when separated by the median.
The whiskers, 10, 50, so this is the median for all the trees that are less than the real.
And the range, there is the range and there's the interquartile range. How we get the range is by getting the absolute difference between the minimum and maximum values.
Or less than older one. This one have if you view median as your central tendency measurement, it's only at 21 years. And you can even see it. It's closer to the left of the box and closer to the left, the end of the left whisker than the end of the right whisker. And ecologist surveys the
Was I right?
closer to the
second, third, first, second, third. Oh no, I'm wrong. First, second, third, below. Oh, I might be right still. I'm not 100% sure.
You might have trees that are between 14 and 20. So I'll call it Q1 for first quartile. Maybe I'll do 121. And so these essentially are splitting. We're actually splitting all of the data into 4 groups. This we would call the first quartile. So I'll call it.
Oh, I see. Okay. I visualized it wrong. That's why we're reviewing, right? So this is quarter 1, quarter 2, quarter 3, quarter 4. You just go by the separation of these horizontal lines. Let's go find the IQR, so interquartile range. Let's see if I've got this. So 11 and 7, 4. Let's see how it's solved. Interquartile range. Oh, 8 and 11, 3. I thought it was 11, 7. Let's restart so we can get the 100%. Find the median data. 6. Find the range. 25 versus 5, 20. Find the IQR. 8.5 and 6. So that's 2.5. Find the median. 6. If we lock in for the rest of the year and don't miss a single week where we still solve at least one problem each week, we should get up to 48 or 44 week streak.
So I have a box and whiskers plot showing us the ages of students at a party. And what I'm hoping to do in this video is get a little bit of practice interpreting this. And what I have here are 5 different statements. And I want you to look at these statements, pause the video, look at these statements, and think about which of these, based on the information in the box and whiskers plot, which of these are for sure true, which of these are for sure false, and which of these we don't have enough information. It could go either way.
Okay, let's think about this. So we have a box and whisker plot. All of the students are less than this. Okay. And then he's gonna put a check mark, I assume, on the right-hand side. So let's go through each statement. All of the students are less than 17 years old. That's a fair assessment because 16 is our maximum value. At least 75% of the students are 10 years old or older. So let me show you why that's true as well. Because we know that these horizontal segments, so this, and this, those are worth 25% each, always in a box and whisker plot. And we can see that here is where Q2 starts. So this is Q1, Q2, 3, and then 4. So Q2, 3, and 4 are at 10 or greater. So that's true as well. There's only one 7-year-old at the party. Okay. We can't determine that because this is a distribution plot as opposed to a frequency plot. What kind of plot is a box plot? frequency plot. But anyways, we can't actually determine what number exactly are the 7-year-olds in this data set, or even the 16. We might know that our max is 16, but what if there's two maxes? That's very possible. So yes, this box plot is a distribution plot, I believe. It's not a frequency plot. A frequency plot would be something like a histogram or a bar chart or a bar graph. And then exactly half the students are older than 13. That's also a fair assessment because, as you can see by Q3 and Q4 and where they start and where they're placed, it's 50% of the box plot dataset, which means that that should be right. Exactly half. Why is it? Don't know. Okay, let's see.
And so it is exactly half. So it's possible that it's true. It's possible it's not true based on the information given. We once again do not know. Anyway, but this possibility up here, we saw that 3, 13, 14. So the next statement, exactly half the students are older than 13. Well, if you look at this possibility up here, we saw that 3 out of the 7 are older than 13. So that's not exactly half. 3/7 is not.
I thought it meant equal to or older than 13. Okay. Let's go. What percent of high schools in Orange County have more than 130 band members? – 0%. Have more than what number of gym members? Also, I need to set a timer because I need to go in an hour because I have an appointment. Have more than what number of gym members? – 70. 105. 25% of Carlson High School teachers have fewer than how many years of experience? Have fewer than 5. Judging outliers in a data set.
We have a list of 15 numbers here. And what I want to do is think about the outliers. And to help us with that, let's actually visualize the distribution of actual numbers. So let us do that. Maybe that's 1, 1, 13, 14. Get the distribution to 1 times Q plus video and try to work through it on your own, or I'll do it for you right now. All right, so what's the median here?
The median is 3, 6, 8, 10, 11. Okay, so we have 15 numbers. So it'd be 8, 3, 6, 8, 14 is the median, right? Yep, this 14. Then the IQR would be between this be here and is that fair? 13, 18, 5. 5 is the IQR.
Well, the median's the middle. Agree that something that's more than 1.5 times the interquartile. Once again, this isn't some rule of the universe. This is something that statisticians kind of say, well, if we want to have a better definition for outliers, let's just agree that something that's more than 1.5 times the interquartile range below Q1, or an outlier could be greater than Q3 plus 1.5 times the interquartile range. Interquartile quartile range. And once again, this is somewhat, people just decided it felt right. One could argue it should be 1.6, or one could argue it should be 1 or 2 or whatever, but this is what people have tended to agree on. So let's think about what these numbers are. 1.5 times 5, which is 7.5. 5.5. So we have outliers. 7.5. 18 plus 7.5 is 25.5. Or outliers, these two ones are, I'll put another outliers on the high side. Now, another thing to think about.
Okay, so you get Q1 and Q3. And then you just stick 1.5 in their quartile range.
Is taking it and
below or above. Then you determine anything outside of that is an
and then to say that
outlier.
we have these outliers, we would put this one where we make it specific, we make it clear where the outliers actually are.
Okay. How many outliers are there in the data set? Okay. So we have 18. It's an even number. So that's equal to 2. Oh, wait, what am I doing? So because it's even, we have two medians. I mean, two middle values, not medians. Okay, 3, 6. What am I doing? How many low outliers are there in the data set? What is our IQR? 8 represents a species of turtle whose average lifespan is 18 years. What? Q1. One given 8. Oh, this is a stem and leaf plot. My bad. 13, 18, 19, 4. This is quite a lot. $37, $38, $40, $47. It is quite a lot for a single question. $138. 369, 369. So the two middle numbers would be 30 and 30, right? So our median is 30, and then we just get the IQR of both halves. So both halves, wait, that doesn't make sense. Interquartile range. Interquartile. 1338, okay. So 24 and 40. 16. I'm not sure if I'm calculating it right. Oh wait, there's a 5-number summary. Oh my god. 16 over 40. Okay. 1, 2, 3. How many low outliers are there? 0. Let's see if we... Yeah, okay. Q3 minus Q1. That is not what I did. 40 and 24. Oh, wait. 16. No, that is what I did. 40 minus 24. 16. Ah, times 1.5. 1.5, okay. 11, 1.5, 16. How many high outliers are there in the data set? Okay. 16. 16 plus, well, that's just 16.5 plus 42. 58.5. A 1. According to the dataset, 1.5 IQR rule for outliers. How many high outliers are there? 5 minus 2 is 3. 3 plus 5 is 8. So there's only 1 high outliers. What? 5 minus 2. 5 minus 2 is 3. 3 plus 5 is 8, right? There are 0 high out. 1.5, not 1. Ah. Okay, the difference is 9. 9 plus 9 plus. No, 9.5. 13.5. 13.5 plus this is 87. 87. There should be 0. Calculator. Plus 933. 1920. 1920. Be 2. I'm kind of confused on how to read this. Number of states. What? 6 times 4? I don't understand how to read this. Hundreds. Ah, I see. Okay, so yeah, that makes sense. Do 2, 1, 3. According to the 1.5, yep. How many low outliers? 13 minus 6 is 7. 7 times 1.5 is 10.5. 10.5. 3, 10.5. 6 minus that. Negative 4.5 is our. Is that right? Feels kind of wrong, but okay. 13 minus 9 times 1.5. 9 minus 6. 3. 3 and below. No. 13 plus 6. 19. Only 1. Just 20. Up next, quiz 3. Let's do only the quizzes for the timestamps, okay? Box plots, quiz. Let's go. What percent of salons in Jamesville employ 18 or fewer stylists? So this is asking based on this box plot, which we know is descriptive of quartiles. We can see these different quartiles. Let me, instead of drawing, just do first 25%, 50, 75, 100%. So this is the first 25%. This is the next 25, this is the next 25, the next 25. So what percent of salons in Jamesville employ 18 or fewer stylists? So employ 18 or fewer. So it's pretty much 100%, right? Because 18 is our max and everything is below that. So 100%. Here's the 5-number summary for these data. And then we're given the min, the max, the quartiles. How many high outliers are there in the data set? So we get the IQR, which is Q3 minus Q1. 13 minus 9. We get 4 times by 1.5. Then we add it to the third quartile to get our upper limit for what we consider outliers. So 13 plus 6, 19. So anything above 19 on our frequency plot, our dot plot over here, would be considered an outlier, and we count that. So we only have one. It's 20. So move on. What percent of gyms in Chainsville have fewer than 56 members? Hmm. Fewer than 56 members. The first quartile is the first quarter of data points, so it should be 25%. But it says have fewer than 56 gym members. What if part of that 25% has 56 gym members? Interesting. Okay. According to the 1.5 IQR rule for outliers, how many high outliers are there in the dataset? Okay, same thing. Q3 minus Q1, 40 minus 24 times 1.5. Then we add it to our Q3 to get the upper limit for what we consider outliers, plus 40. So 64 is our upper limit. How many values over here are greater than 64? And this is a stem and leaf plot, so this is 75, 77, 138, so 3. Then the next lowest value is 47, which is still within the confines of our limits, so 3. About 75% of lakes in Minnesota have more than what number of those boats? Houseboats. So if we draw what this box plot looks like, start with the min. It says it's 12, 18, 23, 26, 29. So how we read this is 25% of data points fall between 12 and 18, then 18 and 23, 23 and 26, and then 26 and 29. So it's saying about 75% of lakes in Minnesota have more than what number of houseboats? More. So on the higher end. So 18 to 23, 23 to 26, 26 to 29, so higher than 18. Cool. What unit is this actually? Unit test 3? Okay. Is this correct course? Go back to math. Whoops. How do you go back? Oh, wait a minute. No, no, we finished that. Okay. Okay. Let's go through each problem, but not take too long. Let's try and allot the next 10 minutes for this. If the mean of the data set is 6 coins, find the number of coins Julia found. So an arithmetic mean can be calculated as, let's call it x, equals sum of some symbol. I'm really bad at this is I equals 1. Alright. Yeah, let's just say some. No, I should use a sigma notation. It was something like this. N equals 1, 2. I equals 1. Of the n, x is I. Let's call it x bar. X bar meaning for the sample mean mu versus x bar. I think they're both I think they're both wrong to use here. But anyways, n. This is just saying even I'm having a hard time understanding this, but the sum, sigma, of all numbers xi for the values I1 to n, which n is the number of the data points in your data set or your set over n, the number of data points. You basically sum your data set and then divide it by the number of points. That's what it's saying. I just wanted to try and challenge myself to express it like this. Anyways, if we follow this, then we know that these are the values of the other numbers. So let's call it x bar still. And let's call the other thing a. A plus 6, 5, 6, 11, 17, 25. A plus 25 over 1, 2, 3, 4, 5, 5. And then we rearrange this equation. So we do 5x bar equals a plus 25. And we move this over, becomes minus 25. Oh, I don't know why X bar is still there. This looks so bad. What am I doing? Okay, let me just repeat the whole thing. 6, 5, 12, 17, 25. Why isn't it? Oh, it's bugging out. I'll solve it on the left-hand side. 25 plus x over 5 equals 6. Oh, right. That's what I was missing. Everything was actually right. So x equals 30 minus 25. X equals 5. Uh, how many low outliers are there in the data set? So it's asking us an interquartile range problem and the outlier problem. So we go show calculator. What is IQR? It's Q3 minus Q1. So minus 42 minus 31, 11. Then from here we do times 1.5. It's asking us for the lower limit of what you consider non-outliers. So you go 31 minus 16.5, 14.5. Ooh. I feel like I did something wrong. 14.5. Oh, it's hard to say. Okay, it's below 15. Let's just say 1. Which interval contains the median date? Oh, 100 pennies. How do we do this again? 55. Say 26. And then this is 9, 5%, 3%. Hmm. Hmm. I want to say it's definitely 2010 to 2020. Has to be right because it's greater than 50%. If each score is increased by 25, what will be the mean and standard deviation? So this is asking us about central tendency, spread, and how they're impacted by manipulating data points or the whole data set. If each score is increased by 25, what will be the mean and standard deviation of the distribution of new scores? If we have a data set of 3, 3, 3, the arithmetic mean is 3, right? Because 3 plus 3 plus 3 is 9, divided by 3 equals 3. If we added 5 to each of them, it would become 8. Standard deviation. Would the standard deviation change? No, the standard deviation would not change. Which of these, the reason why the standard deviation wouldn't change is because the standard deviation is based on the mean. And if we know that the mean isn't going to change, then why would the standard deviation change? Which of these formulas give the standard deviation? It's the one with the squared. What's the difference of these two? Minus 47. Why is minus 47 supposed to be, again, minus mean? Why is minus 8? I think it's this. The mean is 47 halves. Yeah, each thing minus the mean. You get the absolute value. Yep. How will the birth of the fourth kitten affect the mean and median? Okay. Who had a different weight each? There were 3 cats already, between 147 and 159. The cat that weighed 57. How will the birth of the fourth kitten affect the mean and the median? The median would go down. Why? Let's visualize it. Let's say 147, 159. Let's say 150. It doesn't matter as long as we use a number between the data points to validate this. Who each had a different weight. Okay, I was about to say something, but then that statement actually invalidated what I was about to say. So the median in this case is 150, but if we add the fourth kitten, it would go here, 57 like this, because it's lower than 147. Then we would be forced to take the average of these two numbers, which will 100% be lower than 150. So the median would go down, and the mean would go down as well, because it's susceptible to outliers due to the fact that we are using the whole data set to calculate the mean. So the mean will decrease by more than the median. So both of them decrease, but the mean will decrease by way more. The approximate location of the median is in an interval A. The approximate location of the mean is also in an interval A. Would it though? 96, right? See, I'm quite rusty because it's been like 8 days since I've touched this stuff. Not good. Okay, let's try and justify why we think the approximate location of the mean is in interval A. Oh, I know. Right. 10, 10, 55. 55 of them are at least 10. 10 plus, I don't know how much cash I currently had with them. Here's a histogram showing the results. It's 96 divided by this. Surely it has to be in there, right? Okay, we got it wrong. Balance point in interval B. The mean will be typically be pulled towards the skew. That makes sense. Find the IQR of the data in the dot plot. Okay, let's count the data points. 3, 6, 9, 10. So 2 middle values. This and these. Okay. That's middle value of the first half. And so 9 and 12. 3 is the difference. About 25% of quarterbacks in the boys' football league threw fewer than what number of touchdowns? Fewer. Fewer than 7. Order the data sets from largest standard deviation to smallest. Okay, so there's most standard deviation would be this for sure, because they're so far away from the middle. They have the greatest number of data points at the minimum and maximum. And then it would be this, because again, similar to the first, we have a lot of distance from the center. And then this would go at the bottom, has the least deviation, because we have 3 right in the middle. Let's go ahead and solve this again. One, 2, 3, 4, 5. 12 CEOs, 6 and 7. So this would be B, and this would be towards A. They would be the same in this case. This would be A, and this would be B. And this would be B and B, because it's a symmetrical distribution, or so it seems. Are we happy with that, or should we try it again? Let's go. Oh, that's fine. Okay, let's move on to the next. Unit 4. I'll need to go back. Unit 4 start. What time is it? 52, 53. Just say 53. Oops.
The dot plot shows the number of hours of daily driving time for 14 school bus drivers.
Too fast,
Each
I
dot
think.
represents a driver. So for example, one driver drives 1 hour a day. 2 drivers drive 2 hours a day. 1 driver drives 3 hours a day. It looks like there's 5 drivers that drive 7 hours a day. Which of the following is the closest estimate to the percentile rank for the driver with a daily driving time?
Which of the following is the closest estimate to the percentile rank for the driver with a daily driving time of 6 hours?
Of 6 hours. And then they give us some choices. Which of the following is the closest estimate to the percentile rank for the driver with a daily driving time of 6 hours? So pause the video and see if you can figure out which of these percentiles is the closest estimate to the percentile rank of a driver with a daily driving time of 6 hours.
Okay, so there are 14 school bus drivers, right? Percentile rank. Trying to remember how this is done. But 3, 6, 7. And that, so it's above 50% of the data points. So I'll say 55%.
Figure out how, so counting as estimating down. Either of these include the 6 hours right around to the nearest percentile. Now, it looks like the people who wrote this question went with the calculation of percentile, where they include the data point in question. So everything at 6 hours or less, what percentage of the...
Okay. Which interval contains the 35th percentile? Okay, let's do 25 times 0.35 so that we can get the 35th percentile, 33.25. Okay. Okay, so 33.25. We look at the frequencies and see. Okay. 4 plus 2, that's 6. 6 plus 16, that is 22. And then this is 35 or so. So it's definitely 20 to 25, right? Which of the following is the closest estimated percentile for a block of the dry ice with the density of this? We have 15 blocks of dry ice. 3, 4, 7, 7 is 5, 12, plus 1 is 13. Do 12 over 15, 0.8, 86 percentile. Okay, I'll go with that. What interval contains the 48th percentile for this data? 1,000 students. 400 plus 425. Hmm. It would surely be 15 to 20, right? Because it's greater than 400, which is already... Okay, let's go with 15 to 20. Which of the following is the closest estimate to the percentile for the backpack that weighs 31 pounds? Think about it. 31. Okay. 8, 12, 13, 16, 18. Oh, what am I doing? Okay, there's 23 data points below it. So 23 out of 25, 0.92. It's probably... Is that right? 24 out of 25 maybe. 96 percentile. Analyzing a cumulative relative frequency graph.
Nutritionists measured the sugar content in grams for 32 drinks at Starbucks. A cumulative relative frequency graph, let me underline that, a cumulative relative frequency graph for the data is shown below. So they have different, on the horizontal axis, different amounts of sugar in grams, and then we have the cumulative relative frequency. So let's just make sure we understand how to read this. This is saying that 0% of the drinks have a sugar content, have no sugar content. This right over here, this data point, this looks like it's at the point 5 grams, and then this looks like it's at 0.1. This says that 0.1, or I guess we'd say 10% of the drinks that Starbucks offers has 5 grams of sugar or less. This data point tells us that 100% on 15 grams on our, but at this point right over here, what has a cumulative relative frequency of
I see.
0.5?
Estimate the percentile of the strength to the nearest whole percent. 15 grams of sugar. So over here, we will go with 0.2. 20th percentile. 25. What is the best estimate for the IQR? So we'll go with 20. 25th and 75th. So that would be, right, best estimates for the IQR of the distribution of three drinks. That seems to be like 17.5 and 37.5. That's 20. Let's go with 20. Okay. Z-scores. Z-scores. Okay.
One of the most commonly used tools in all of statistics is the notion of a z-score. And
why is it called a z-score?
one way to think about a z-score is it's just the number of standard deviations away from the mean that a certain data point is. So I'm going to write that down. Number of standard deviations. I'll write it like this. Number of standard deviations.
What is the standard deviation formula again? It's something over the number of data points. And you sum stuff, you square the stuff. Standard deviation formula. Yes.
From our population mean for a particular data point. Now let's make that a little bit concrete. Let's say that you're some type of marine biologist and you've discovered a new species of winged turtles. And there's a total of 7 winged turtles. The entire population of these winged turtles is 7. And so you go and you're actually able to measure all the winged turtles. There's another 2 centimeter one. There's a third of the winged turtles.
Okay. How do we calculate standard deviation? So we need to get the mean first. And then we get the sum of how do you even say it? You get the sum, so that's sigma notation. You get the sum of every data point minus the mean squared. And you have to get the absolute, the squared will get the absolute value.
Well, that is approximately, I'll round to the hundredths place, watch this video and see if you can do that. So let me make a new column here. So here I'm going to put our z-score. And if you just look at the definition, what you're going to do for each of these data points, let's say each data point is x, you're going to subtract from that the mean, and then you're going to divide that by the standard deviation. The numerator right over here is going to tell you how far you are above or below the mean, but you want to know how many standard deviations you are from the mean.
Yes.
So then you'll divide by the population standard deviation. So for example, this first data point right over here, if I want to calculate its z-score, I will take 2. From that, I will subtract 3, and then I will divide by 1.69. I will divide by 1.69. And if you got a calculator out, this is going to be -1 divided by 1.69. And if you use a calculator, you would get this is going to be approximately -0.5.
So it's the individual data point, x at I minus mu over standard deviation.
5.9.
Fair enough.
And this do a simple 9.
And
this, if you have a calculator, and I calculated it ahead of time, this is going to be approximately 1.77. So more than 1, but less than 2 standard deviations above.
And then you do that for every single
inferences
thing.
based on our data. So I will leave you there. Just keep in mind, it's a very useful idea, but at the heart of it, a fairly simple one. If you know the mean, you know the standard deviation. Take your data point, subtract the mean from the data point, and then divide by your standard deviation. That gives you your z-score.
So there's a z-score for each data point. Okay. The grades in a math midterm at Springer are roughly symmetric with this and that. Brandon scored 71 on the exam. Find the z-score for Brandon's exam grade. Round to 2 decimal places. Okay. It was mean. It was exit I plus mean over standard deviation. 68 plus 71 divided by 4.5. 30. Did not. This is surely wrong. This is so wrong. Okay, 30.9. Round to 2 decimal places. 89. No. What am I doing? Okay, let's try and figure out. What did I do? 68. Oh, no. 71 minus 68. No, 68 minus 71. No. 71 minus 68. 4.5. 0.67. Ah. Yeah. Minus 74 minus 72 is 2. Divided by 2, that's 1. 86 minus 85 is 1. 1 over 2 is 0.5. 66 minus 68 is minus 2. Minus 2 over 5.5. 0.36. 65 minus 69 over 3.5. Negative 1.14. Okay. Use standardized scores, also called z-scores, to compare data points from different distributions.
Before applying to law school in the US, students need to take an exam called the LSAT. Before applying to medical school, students need to take an exam called the MCAT. Here are some summary statistics for each exam. So the LSAT, the mean score is 151 with a standard deviation of 10, and the MCAT, the mean score is 25.1 with a standard deviation of 6.4. Juwan took both exams. He scored 172 on the LSAT and 37 on the MCAT. Which exam did he do relatively better on? So pause this video and see if you can figure it out.
Hmm. Let me think. Hmm. I would say that he would have done better. Z-score. Data points from different distributions. 151. What is the z-score formula? X at I minus u mu over 10. We can turn that into x over 10 minus 151 over 10, so 15.1. I don't know. I would say he done better on the LSAT because mean and standard deviation works around the mean, right? And so if we look at this proportionally, this is not even 10% of the mean. So worst case scenario, it's unrealistic that. Oh wait, he scored 172 on the LSAT and 37 on the MCAT. Oh, which exam did it? I had the wrong understanding of the question. Okay, give me a sec. I didn't fully read it. So we just get the z-score for both. To know his standardized score. So it's almost like what percentile, what relative to the average student did he do better on? So 172 minus 151, that's 21. 21 divided by 10 is 2.1, so that's his z-score for LSAT. Pretty good. And then for the other, it was 37 minus 25.1, which is 11.9, divided by 6.4, which is 1.5 or something. I don't know. Okay,
So the
I
way I
forgot
would
the
think,
first value
he scored
anyways.
up to scored a
Oh
37.
yeah, okay, he did better in
The
the LSAT.
give it on the LSAT to the nearest, since he comparable. If this was 3 standard deviations and this is 1 standard deviation, then you'd be like, oh, he definitely did better on the LSAT. This can see more standard deviations, although this is close. I would say they're comparable. He did roughly, it's approximately 1.86. So approximately 1.86. So relatively speaking, he did slightly better on the LSAT. There's more.
Yep. Which plant had a better harvest? Okay, let's use a calculator. 9 acres of soybeans, 3,000 acres of peanuts. Again, z-score formula. Exit I minus mu divided by standard deviation. So this is our first one. Then exit I minus mu over standard deviation. What did better? The first one. So 9,000 acres of okay, so soybeans did better. Let's look at our things. Soybeans, peanuts, equally good harvests. Impossible to say without seeing all of the harvest amounts. Impossible to say since we don't know the shape of either distribution. Let's go with that, I guess. Okay, the soybeans better. See, it's impossible. Uh, okay, it was a trick question. I don't think that's ever the answer. Okay. 20 minus 22 divided by 5. 33 minus 38 divided by 12.5. The same. The first one is 30 minus 25 divided by 2.5. 2. 88 minus 95 divided by 7.5. Which candle burned faster? Okay, we'd go with the second one. 88. Second candle. Berry candle. Relative to other sleeping bags. Okay. 15 minus 21 divided by 11. That's our first one. Negative 0.54. Then 29 minus 32 divided by 12.9. Ooh, The first one did better. Oh wait, lower. 15, 20. Oh wait, I had a typo. 29 minus 32. Negative 0.2 versus negative 0.5. Okay, the first one, definitely. Juan took both exams. He scored this and that. Where did he do better? Okay, 2.1 versus he did better on the LSAT. Give me a second, guys. I'm just stretching out. Time check. Time is it? 1:15. Calculate the standardized Z-score. Whoops. (18) versus 14. So 14 minus 18 is -4. -4 is 80% of 5, which makes it 0.8, and -0.8. What is the best interpretation of the z-score? Well, the z-score is the number of standard deviations below or above the mean. So it says below the mean there. A different coffee shop below Ruth's Roasts. Ruth's Roasts serves drinks that contain a mean of 16 grams of sugar with a standard deviation of that. Grande Mocha. 13 minus 16 is -3. -3 is -0.56. So it has relatively less sugar at Jake's Java. How much sugar is a grande cappuccino at Ben's Beans? What are these names? Jake's Joe's, Ruth's Roast. Oh my god. Okay. Drinks at Ben's Beans have a mean sugar content of this. Oh, this is reverse. To the rest of the drinks at the shop. Okay, so the formula to get the standard deviation is exit I minus mu, the mean, over 6. But in this scenario, we'll pull out the trusty frickin' just do it here, guys. Shift F, Control F. It would look something like this. Why is it so blurry? Okay. We need to solve for exit I. Minus 20g over 6. Negative 0.75 is our z-score. So we would end up with oh my goodness. It sucks. Times 6 plus 20. 15.5 maybe. Easy. Let me just see my travel time because I need to go meet up with a friend as well. He broke his ankle, so playing basketball actually. Lloyd's Clinic. 37 minutes. How many? Let's see how far we've gotten today. Could come back. 37 minutes. Oh, I need to go. Yeah, I'm gonna be late. It's one of the things that I'm working on, so I will be back and we'll probably go for another hour or another 30 minutes when I'm back, but we're up to 120, an hour and 20. So let me just clean this up. And I will pause this. See you guys in a bit.
And I'm back. Okay, where were we? We're on to quiz 1. What was the last thing we were doing? Z-scores. Okay, how do we calculate the Z-score? It was... It was mean, standard deviation, and... Was it IQR? We'll figure it out. Okay. What interval contains the 60th percentile for this data? Okay. Summarizes the number of tropical storms per year in the US for 30 years. Hello? Okay. Contains the 60th percentile for this data. 30 times 0.6. So above 0, 10. Okay. Let me just do the math. 1 plus 7 plus 5. How many is that? 13. Plus 4, 17. Then 18 is here, right? So it's 100 to 125. Relative to its type, what candle burns faster? Then this is 30 minus cinnamon scented jar candle. 30 minus the mean divided by the standard deviation. That's a z-score. 288 minus 95 divided by 7.5. That's a z-score. So a smaller z-score in this scenario means that it burns less than the mean. So the second one burns faster. Berry scented clear candle. Okay. Find the z-score for Michael's exams grade. Okay, so the given grade minus the mean grade over the standard deviation, which is 2, 0.5, means that it's 0.5 higher than the mean. Makes sense. Which of the following is the closest estimate to the percentile for the donor who is 24 years old? Okay, so close estimate to the percentile for the donor who is 24 years old. This is a stem and leaf plot, so it's organized in ascending order. So we start with 19, 21, 24, etc. So we just want to see, so this is the 1, 2, 3, the third value, the third lowest value in the data set of 25. So we do 3 over 25, and we get 0.12, which is the 12th percentile. Okay, and then this is another problem asking us to compare relative z-scores. or relative positions in two different data sets. Okay, so it says we have a beginning and the end sleeping bag, so two different sleeping bags, and we want to get the z-scores for both. So we do 15 minus 21. The given score minus the mean score. In this scenario, it's 21 divided by 11. That's z-score 1. Then the next is 29 minus 32, which is the mean, divided by 12.9. And then the question is, so we have both z-scores now. Relative to other sleeping bags, which of the sleeping bags had a relatively lower rating? So the first one is negative 0.5, the second one is negative 0.2, so the first one is lower at the beginning of your trip. Okay, lesson 3. Density curves. Time 1:26. Of all of my video series, this is probably my favorite because it's so straightforward and so chill.
How to visualize distributions of data, and then to analyze those. But let's start with a simple example, just to review some concepts. Let's say I go to 16 students, and I ask them to measure how many glasses of water they drink per day for the last 30 days.
Okay.
And then to average it.
To average it, you would get the sum of the data set. It's a sigma where I equals 1, and you go up to n.
And so this
and then you just add everything.
Data point right over here tells us one student drank
equals xi
0.5 glasses of water per day. That person is probably very dehydrated. This person drank 8.1. Setup would be for data points that are greater than or equal to 0 and less than 1. And we can see that 2 data points fall into that category, and that's why the bar right over here for that category is up to 2. This category right over here is greater than or equal to 3, and this frequency histogram. You might be more concerned with what percentage of my data falls into each of these categories. And that becomes especially interesting if we have many data points. And if we had, 1,600,000,430 useful, the percent that fits into each category is a lot more useful. And so for that, we could set up a relative frequency histogram. So notice, this is representing the same data. But in that first category, instead of the bar height being 2...
Okay, so simple enough. The only difference this would be is that, say 12.5 or 25%, 4 is 25%. So how many data points we have here? We have 1, 2, 3, 4, 5, 6, 7, 16 data points. Yep.
The bar height is now 12 point.
So we're just representing this with a percentage instead of a discrete number, discrete value.
Percent. Instead of the height being 4 for data point histograms are really useful, and you will see them used all of the time. But there are also cases where you have many more data points, and you want more...
Give me a second, guys. Okay, I'm back.
Granular categories. So what you could do is, well, let's just make our categories a little more granular. So for example, instead of them being 1 glass of water wide, maybe make them half a glass of water wide. So this first category could be greater than or equal to 0 and less than 0.5. And that will give you a clearer picture. And I'm now assuming each category.
Okay, let's just zoom through this because it's not... Oh, okay.
Is the density curve data points. Maybe we have... Because 2 of the 16 data points fall into this category. 2/16
Changed my mind. I think this is something that I want
this one right over here, notice, instead of the height
focus
being 4
on just a bit more.
4 data points, it's now 25%. But these are saying the same thing. 4 out of the 16 data points histogram, more data points. Let's make our categories a little more granular. This first category could be having an infinite number of categories, and each category is infinite curve. And this type of curve is something that we actually use in statistics. And as promised at the beginning of the video, this is the density curve we talk about. Points can take on any value in a continuum. You look over the entire interval, 6%, or the curve is 1. See the curve dip down and do something strange like that. The curve will also never take on a negative value. You won't see the curve dip down and do something strange like that. Now, with that out of the way, let's think about how we would make use of it.
Whoa,
if I wanted to know what percentage of my data falls between 2 and 4 glasses, and I would try to figure out the area under the curve equal to 100%. When I'm just eyeballing it, I would say roughly 40% of my data fall great useful. In the real world, statisticians will often have tables that might represent the information for the density curve. They might have computer programs or some type of automated tool. And there are also well-known density curves, the famous bell curve that we will study later on, where there's a lot of data is exactly 3 glasses of water per day. And when I say exactly, I mean exactly the number 3.000 with zeros just going on and on forever. It's like approximate data water 0.15 maybe. So now we have an interval that actually has width. And so it'd be roughly the size of this yellow area that I'm... Hey, look, we're going from 2.9 area.
Okay. I said the thing. I've said it multiple times throughout this video, just haven't called myself out. Mean, median, skew.
In other videos, we introduce ourselves to the idea of a density.
Okay, this is pretty straightforward. If the median is the middle value, the mean usually sits towards the skew, quote-unquote balance point. Left skew, right skew, bimodal. Right skew is when it's skewed to the right, left skew is when it's skewed to the left or has a left tail. This is normally distributed. It's a bell curve. And then this is a bimodal distribution. It has 2 local middles or modes.
Density curve. We'll talk about this. If we unleash this, will be estimated. You might be over to the right rather than the left area. So that would do that. It's pretty clear, even eyeballing it, that the right area, right over here, is larger than this, maybe right around here. This looks a lot closer. Once again, I'm approximating it, but it's reasonable to say that the area here looks pretty close to the area right over there. And if that is the case, then this is going to be the median.
Median, yeah.
For you weight method, which you would want to weight of then. This is me approximating it, but this median is referring to balance it out.
So they're both skewed, but the mean is skewed more.
Right, distribute under these as left skewed.
Qualitative sense of normal distributions.
You can never have too much practice dealing with the normal distribution, because it's really one of those super important building blocks for the rest of statistics, and really a lot of your... You can never have too much practice dealing with the normal distribution, because it's really one of those super important building blocks for the rest of statistics, and really a lot of your life. So what I've done here is I've taken some sample problems. This is from CK12.
I thought my microphone was
open
bad.
source flexbook, their AP statistics flexbook, and I've taken the problems from their normal distribution chapter, so you could go to their site and actually look up these same problems. So this first, we believe they would not follow. So I think it's kind of an essay question. So let's see what they have here. A, the handspan measured from the
Which of the following data sets is most likely to be normally distributed? For the other choices, explain why you believe they would not follow a normal distribution. Okay, essay questions. The handspan, the annual salaries of a random sample of 50 CEOs. The dates of 100 pennies taken from a cash drawer in a convenience store. Okay, so I'm trying to recall, but the central limit theorem implies that if a value has multiple predictors, and the more predictors it has, if you were to get a random sample of said value, you would likely run into a normal distribution if you have enough data points. But let's see.
I think they're talking about that distance right there. And they're saying, if I were to measure it of a random sample of high school seniors, what would it look like? Well, you know, how far this is a combination of genetics and environmental factors, maybe how much milk you drank, or, you know, how much you hung from your pinky from a bar while you were growing up. So I would think that it is, you know, a sum of a huge number of random processes. So I would think that it is roughly normally distributed. You know, if I look at my own hand, and my hand, I don't think has grown much since I was a high school senior. It looks like, I don't know, it looks like roughly 9 inches or so. I play guitar, maybe that helped me.
I'm really proud that I knew that.
But if that's, you know, it's really an essay question, so I just have
He's
to say
not
what I
saying
feel.
central limit
So I would
theorem,
guess that the distribution would look something like this. Something like perfect. In fact, I could make maybe distribution on the left-hand side. That's you know, what liars or seniors. When I did this, it was kind of from my pool distribution, maybe off like part A, a large shipping company. So if we're talking
large shipping company, again, male, female, different roles, different times at the job, different risks, different
annual salaries. You know, we have minimum wage laws, whatnot. So, and probably a lot of people will have that minimum. And then you have your different middle-level managers and whatnot. And then you probably have, you know, this big gap. And then you probably have your true executives, maybe your CEO or whatnot. With you know, if this mean right here is maybe 40, this out, you know, over here. It definitely wouldn't be a normal distribution, and it definitely would have a second. It would be bimodal. You would have another peak over here for senior management up at the unless where you're not going to go right skewed to distribute a lot of annual wrote this year. I think they maybe are implying that
Annual salaries of random sample of 50 CEOs of major companies, 25 women, 25 men. I would say it's probably normally distributed.
maybe, well, they're really getting to some gender two, one hump for women, and if you assume women are less than men, then another hump for men. And they're 25 of each, so there wouldn't be necessarily more men than women, and then it would skew all the way off to the right. And in fact, I think there'd probably be a chance that you have this other notion here where you have these, super CEOs or mega CEOs who make millions, while most CEOs probably just make, just up in quotation marks, a few $100,000, while there's a small subset that are way off many standard deviations to the right. So it could even be a trimodal
So it's basically
distribution
the
here.
same
So let's see
question.
what D is.
The dates of 100 pennies taken from a cash drawer in a convenience store. Oh, well, there's so many possible 100 pennies, and so I'm
of
guessing
100,
that
I
should
would
be normal.
last 9, say
Maybe.
the United States, or before they even started printing pennies. So it's obviously the
Oh, okay.
scale is going to go huge. Sometimes the end. So for the but I would say choice.
That was kind of intense, to be honest. He was like the detective Sherlock Holmes.
Let's do another problem from the normal distribution section
Sorry
of
if I sound like Megatron, by the way. I have the fan turned on.
CK12.org's
It's really
AP
hot.
statistics book, and I'm using this because it's open source. It's actually quite a good book. The problems are, I think, good
Okay, draw a sketch and shade the proper region for each problem.
practice for us. So let's see. Number
Distributed with a mean of about 9.5 grams, the standard deviation of approximately 1.1. Without using a calculator, estimate the percentage of 1-year-old girls. Okay, so down here it says 68, 95, 99. Approximately one standard deviation to the left and right covers 68%. Then if you do another left and right, one more standard deviation, it would be 95, and then you do one more, it would be 99.7. This is assuming that your data follows a normal distribution. So let's see.
3. Number 2, you could go to their side 99, one standard deviation. The probability of finding a result, if we're dealing with a perfect norm, get something about above guess it, 95. Empirical rule, standard hard to do. I'm not deviation point above 7, 1 point. So that's this area right here.
And obviously, if you only want to go between one way, you can just take the other or half it or whatnot. Okay, next exercise. Empirical rule. Oh, that's what it's called, the empirical rule. Rule 137. To estimate the probability of a seal living less than 7.4 years. So let's just draw this out. Average seal lives 13.8 years, so 13.8. Then let's draw the bell curve. Beautiful. And then we have the 68 like this. And then 95, and then 99.7. So it says estimate the probability of a seal living less than 7.4 years. So the standard deviation is 3.2. So over here it would be 10.6. Then here it would be 7.4. So it's asking us what this shaded region is. So you know that this is 68 and 95. And the remaining here and there is 99.7. So all we have to do is do 100. Hold on. We would calculate this area, right? Wait. 98, 95, 99%. Huh? 68, 95, 99.7. Yeah, okay, so we would calculate the area of these 2 bits, but then we would just half it because we're only considered with the left-hand side. And because it's symmetrical, that's why we can half it. So it would be 99.7 minus 5 minus 95, then divided by 2. Then this would be the percent. So 5, 0.52%. No, wrong. Okay, let's just see the hints. 2.5%. I felt like my graph was kind of off, but fuck. Okay. Oops, I swore. 1. Okay. $20.8 minus 1 times 3. That's 3 standard deviations to the left and 2 standard deviations to the right. $68. 95. 99.7. Between 11.5. Okay, so 1 deviation, 2, 3. So over here, 20.8, 3.1, 3.1, 3.1. Okay. And 2 deviations to the right, so here. Okay. Okay, now I think it makes sense. So we do 95 because we want this whole thing. Then we do 95, the difference between 95 and 99.7, and then you get half of that. Then add that onto 95. Plus 95. 97.35%. Yeah. Use the empirical rule, 68 minus 95 minus 99.7 to estimate the probability of a tiger living longer than 14.3 years. Turn off the fan. Okay. 14.3, well, 22.4 minus 14.3 divided by 2.7, 3. It's 3 standard deviations to the left. Okay, so 1, 2, 3. 1, 2, 3. So it would be this, 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 and then greater than this pretty much. Okay, well, 68, 95. That's not even the correct amount of freaking lines. Oops. Ah, this is so trippy. Okay, so it's 3 to the left. 1, 2, 3. So here, over there. Okay. 65, 95, 99.7. Okay, so it'd be 99.7 plus the remaining on the right hand side, right? 99.7, 99.85. To estimate the probability, okay. It's one standard deviation to the left, so it would look like this. 67%, 95%, 99.7%. So it'd be here, and then shade this entire side. Okay, so this is 68. Okay, so we know half of that is 50%, right? And we know that this is 68%. So we just need to get half of this, which is 34 plus 50%. It's 84%. And we're curious to see what the remaining is, so do 100 minus 84, that's 16%. Okay, so here it's asking us between one standard deviation and 2 standard deviations. Okay, so we know that this area is 68%, and we're curious with this bit of the line. And we know the next bit is here, the broken line is 95%. So what we could do is, hmm, hmm, don't know why I did that. Okay, I'll just draw it again. So it's like that. The broken line is 95%, and this unbroken line is 68%. So what we could do instead, and we actually want this segment. We can get this half by doing 95 divided by 2, and then adding the remaining left hand side, and we can get that by doing 68 divided by 2. 68 divided by 2, 81.5%. Hey, nice. Many measurements fit a special distribution called the normal distribution. And normal distribution, yep, okay. This one. What? 100, 105, and 135. Huh? Explain. 105. Wait. Oh, I was looking at the wrong thing. Okay, next lesson.
A set of middle school students' heights are normally distributed with a mean of 150 centimeters and a standard deviation of 20 centimeters. Darnell is a middle school student with a height of 161.4 centimeters. What proportion of student heights are lower than Darnell's height? So let's think about what they are asking. So they're saying,
Yep, so this is normal distribution with a mean of 150, standard deviation of 20. Darnell is a middle school student with a height, blah blah. What proportion of students' heights are lower than Darnell's height, which is 161.4?
saying that heights are normally distributed. What curve, right? What the definition is, and we know the difference between Darnell's height and the mean height. And then once we know how many standard deviations he is above the mean, that's our z-score, we can look at a z-table to tell us what proportion is less than that amount in a normal distribution. So let's do that. So I have my TI-84 emulator right over here. 150 minus 107.4 divided by 20. So we will just take our previous answer. So this just means our previous answer divided by 20 centimeters. And that gets us 0.57. So we can say that this is 0.57 standard deviations
Right.
above the mean. Now, why is that useful? Well, you could take this z-score right over here and look at a z-table to figure out what proportion is less than 0.57 standard deviations above the mean. So let's get a z-table over here. So what we're going to do is we're going to look up this z-score on this table. And the way that you do it, this first column, each row tells us our z-score up until the tenths place. And then each of these columns after that tell us which hundredths we're in. So 0.57, the tenths place is right over here. So we're going to be in this row. And then our hundredths place is this 7, so we'll look right over here. So 0.57, this tells us the proportion that is lower than 0.57 standard deviations above the mean. And so it is 0.71.
And if you want to go higher, then you just do 1 minus that, right?
57, or another way to think about it is, if the heights are truly normally distributed, 71.57% of the students would have a height less than Darnell's. But the answer to this question, what proportion of students' heights are lower than Darnell's height? Well, that would be 0.7157. And they want our answer to 4 decimal places, which is exactly
Standard normal table for
a set of philosophy exam scores are normally distributed with a mean of 40 points and a standard deviation of 3 points. Ludwig got a score of 47.5 points on the exam. What proportion of exam scores are higher than Ludwig's score? Give your answer correct.
Okay, give me a second, guys. I'm gonna take a nap. Back, fellers. That was a nice nap. Now, let's do some stuff. A set of philosophy exam scores are normally distributed with a mean of 40 points and a standard deviation of 3 points. Ludwig got a score of this. What proportion of exam scores are higher than Ludwig's? Okay, so from memory, before I took my nap, we learned about the z-score table. So, let's see. Oops, Facebook. Z-score table. So we know the mean, we know the standard deviation. We can get the z-score and then see what proportion are lower, then minus that by 1, then that's what's higher. So we know that the mean is 40 and the standard deviation is 3. We can get the z-score. That would be 47.5 minus 40. That's 7.5. 7.5 divided by 3 equals 2.5. So the z-score is 2.5. Makes sense. So we go here, 2.5, 0.9938. 1 minus 0.9938 equals 0.0062, which is 0.62%.
To 4 decimal places would look symmetric looking. Deviation it is that is above right with 4. We through the z from columns give us there's no so right over is lower than So what I'm going to then loop a over 2 standard deviations, all 2.5.
Geez, I'm good. Okay. It feels like my voice when I have energy versus when I don't is really different. I'm just saying. Let's go. Lower. Okay, so we get the z-score. So it's 161.4 minus 150 divided by 20, 0.57. That's how many z-scores. Then we go 0.57 and say in lower, so 0.57. We go here. Then it's lower, so that's the answer. 0.7157. 0.7157. Boom. Easy. It's crazy what a 40-minute nap will do for you. Okay, and then same thing. Get the difference, then the z-score. So 20.66 minus 26 divided by 2. This is it. What's lower than this? So we just get the actual value. Negative 2.67. So go here and here. 0.0038. What proportion? Oh, whoops. Oh no, that's correct. Wait. Is it asking for a percentage? In that case, it might be that. I'll show a step hints. 2.67. No, I got bamboozled because it says the average temperature, so I assumed that was the mean. Okay, let's go repeat this. Let's go. What proportions of bed prices are higher than the price of the wooden bed? Okay, 99. That's our observed value. 1300 is our mean. Then we do what? Minus 1300 divided by 300. And then we go here, higher, 0.33. Then we go to here, 0.3. Go here, 0.6293. 0.6293. 1 minus that equals 0.3707. What proportion of piano prices are higher than the price of the electric piano? Okay. Electric piano is 2576. So it's lower. Then divide by 200. That's our z-score. Then we see what proportion are higher than the z-score. So we do 1 minus negative 2.12. 1, 2, 1 minus 0.017, 0. 0.983. What proportion higher than Uma's height? Uma's height is 165 minus 150. Minus 150 divided by 20. 0.75. 1 minus 0.75. 0.7734. Wait. Yep. 0.7734. 0.266. Just like that. Check. Higher. Okay, leather sofa versus mean sofa. So 2410 minus 2500, so it's lower. Makes sense. Divided by 200. That's our z-score. Then it's asking higher than the z-score, so we're going to do 1 minus something. Negative 0.45. Negative 0.45. Whoops. Negative 0.45.
by here, 0.3264. 0.3264. That's our answer. Anyways, we've hit 2 hours exactly, and I feel like I could keep going, but I think we're gonna leave it there so that I can shoot another video and clear math out of my head and then come back to it. So let's just close the video and talk about some stuff. The closer. Closing message. Let's just go back and quickly recap what we've done so far. That's something I used to do in the earlier videos, but as of late, I haven't been. We started with Unit 2, I believe. No, Unit 3. Yeah, it's been... Interesting. Surely we've... Ah, well, it's fine. Oh, wait, here. Math begin box plots. The first thing we did was box plots. Somewhere here, I think we did the unit test and then we went straight into percentiles, but that would not make sense. Well, anyways, okay, closing message. Time check. 2:01:25. Let's look at our sticky notes. So I swore once. I probably violated these more, to be honest, so just scrap this. I said "okay" multiple times. I swore once. And I probably might have said or like a couple of times in the video, but we'll take it seriously in the next. Haha. Go on. Done for now. So anyways, remember what I told you guys at the beginning of the video. Often we're unaware of our own unawareness. Oh my God, let me say that again. Often we are unaware of our own unawareness. That's why it helps to have a group or like-minded individuals to check you, and it's important to check yourself as well because you can always do that. This isn't the death sentence, it's more of something we have to keep in mind while we navigate through our lives. And this is the first great fall, you could say, for my YouTube channel. But we'll come out smarter, stronger, more powerful than ever by the end of it. Just like in One Piece when Zoro got owned and schooled by Mihawk for the first time, that was a pretty big revelation for him. So I might make another video talking about my 2025 goals, but in all honesty, 2025 is going pretty good. Off to a strong start. The vision, the goals, they're so clear in my head, and I can't help but just enjoy myself, I guess. And I'm glad that I get to share this journey with you guys. I can't wait to be able to look back. I already am able to look back and say, oh man, remember in season 1, episode 1 of Speedrunning Math Calculus when we were doing the frickin' arithmetic and the PEMDAS and all the super basic stuff. Logarithms and exponential form. We've learned so much through our journey so far together, and I really like that. I don't know if anyone really watches these videos, but I hope you feel inspired because I inspire myself to keep on learning and keep on growing. There are so many unintended and unexpected things that have happened with the channel so far and my learning process that I hope people
take away from my journey positive things and realize how much they're capable of as individuals. My channel isn't anything revolutionary. I didn't invent rocket science creating this channel, but you don't have to invent rocket science. You don't have to invent physics. You don't have to be Elon Musk. It can be just as simple as doing great things that you have not done in the past. Doing new things, doing bigger things, expanding your universe. So anyways, that was just a motivational rant to end the video off, which I used to do a lot, but as of late, I feel like I've just been waffling, and so I've felt a bit more insecure and a bit shy to waffle on like this. I think waffling is okay. Anyways, thank you for watching, and I will see you in the next video.